Hello, back again. Chapter 2, we're in section 2.5, the atom composition. And as we had said before, Rutherford discovered that the atom was mostly derived of empty space. And so if we're looking at our atom, we have a very small, positively charged center, the nucleus in the atom, and then the electrons will be orbiting around that nucleus in some type of pattern, which we're going to look at. Now, what we'll see with the video here is, again, if you're clicking on these videos, which is a really good thing to do, you're going to see that this talks about the atom.
Hi, I'm Emerald Robinson. In this What Is video, we're going to take a closer look at atoms. All matter is made of elements, substances that cannot be broken down by chemical activity. An atom is the smallest particle of an element that retains the element's properties. Atoms are the building blocks for everything in the universe, including ourselves. People often think of atoms as the smallest possible forms of matter, but even smaller particles make up atoms. Each atom has a dense center called a nucleus. The nucleus contains neutrons, which have a neutral electric charge, and protons, which are positively charged. The number of protons in an atom determines an element's physical properties. No two elements have the same number of protons. Revolving around the nucleus like planets around the sun are negatively charged particles called electrons. Electrons and protons attract each other, so atoms usually have equal numbers of the two particles. Scientists assign atoms an atomic number and atomic mass unit. The atomic number is the number of protons present in the atom. For instance, a helium atom has 2 protons, so helium's atomic number is 2. Add the number of protons and neutrons in an atom's nucleus together, and you get the atomic mass unit, or AMU. A helium atom has 2 protons and 2 neutrons, so has a mass of 4 AMU. Electrons have almost no mass and are not included in AMU calculations. While an atom's number of protons remains constant, individual atoms can lose or gain electrons. Atoms with different ratios of electrons to protons are called ions. Atoms of the same element can all...
So we're going to be talking about ions a little bit further on in this chapter. So if you're like, what is she talking about right now? We are going to get to the ions.
Also have extra neutrons. Scientists call atoms with extra neutrons isotopes. Despite having different neutron counts, isotopes retain their element's chemical properties because the number of protons remains constant.
For thousands of how-to and advice videos.
Okay, so back to our slideshow here. So we have our protons and our neutrons in our nucleus, and as she said, for neutral atoms, and that means that atoms that don't have an overall electrical charge, the number of electrons is going to be equal to the number of protons, and that's going to be really important. So we want to remember that one. And then, of course, our electrons are going to be outside of our nucleus here. And so we're going to be reading section 2.5 about the proton. And so essentially it's almost 2,000 times the mass of the electron, and that's why we say the electron basically has a mass of 0 AMUs. Now the number of protons inside an atom is called the atomic number. It's also called the Z number, okay? And so elements, what we'll find is atoms of the same element all have the same number of protons, and so they have the same Z number. And so we can have carbon 12, and this is the mass, and we're going to be looking at this during our rest of the PowerPoints, but this is the atomic number, the Z number. So it's atomic number 6. It has 6 protons, but we may be walking down the street and meet carbon 13. It has a slightly heavier mass, and it happens to be radioactive. Versus just normal carbon 12. But you'll notice it has the same Z number in that they both have the same number of protons. And we'll look at that. Now the neutrons don't have any electrical charge, and in order to determine the number of neutrons inside an atom, we need to look at the mass number, which is called A. Don't ask me why mass number is not M, or why atomic number wasn't the letter A. Okay, mass number is the letter A, and so it is going to be equal to the total number of protons plus the number of neutrons inside of the nucleus. Now, what we'll see is Dalton had said all atoms of the same element are identical. And he was wrong in that because he did not know about the existence of what are called isotopes. And an isotope, they are elements of the same, or atoms of the same element, meaning they have the same number of protons. So we have carbon-6 has a mass of 12, carbon-6 has a mass of 13. So here the A number is 13, here the A number is 12. And so what we'll find is both of these atoms of carbon have 6 protons. But what's different is their mass. And so they differ by the number of neutrons. And so if we were to look at carbon 13, if we were to take the mass and subtract the Z number, the number of protons, so if we were to take A minus Z, we're going to get the number of neutrons inside of the nucleus. And so for this guy, he has 7 neutrons, whereas this guy has only 6. 12 minus 6 is 6. And so they only differ by the number of neutrons inside of their nucleus. So if we're looking at some funness, and as you know, are going to find out, I am addicted to YouTube.
Hi, we haven't seen you in here before. What's your name?
I'm a neutron.
Say, that's an unusual name.
I'm a subatomic particle. I come from the nucleus of an atom.
Would you like another drink?
Sure. How much will it cost?
For you? No charge.
Is that supposed to be funny?
Get it? No charge? Haha. Anyway. So, on that note, let's get out of there. So back to our PowerPoint. Now, a nuclid is looking at this symbol, what is inside of the nucleus, and it is characterized by the number of neutrons and the number of protons inside the nucleus. So when we're talking about the number of nuclids in something, we're talking about how many neutrons plus how many protons are inside of our nucleus. And so you'll see here with our atoms, in this one we have 23 nuclids. There are 11 protons inside the nucleus and 12 neutrons, 23 minus 11, so there's 11 protons. Whereas lithium has 7 nuclids. Its atomic number is 3, so there are 3 protons and 4 neutrons. 7 minus 3 is 4. And so we'll see that we can look at how many particles are in the nucleus of each of these isotopes. So the mass is always rounded off from the periodic table. So in our periodic table, the masses are never whole numbers, so you're going to round those off, okay, in order to write the isotopic symbol. And then, of course, our atomic numbers are always whole numbers. So it says write the nuclid symbol for an atom that has 19 protons and 20 neutrons. So first of all, the atomic number, the Z number, is 19. Now, how many nuclids are there inside the nucleus? Well, how many protons and how many neutrons are there added together? Well, there's 39. So the mass number will be 39, 19 plus 20. And so all we need to do is be left to look up what is element number 19 on the periodic table. So if we look that up, the element is potassium. And so if we were to write the nuclid symbol for this, whoops, we have 39 upstairs, we have our 19 downstairs for our atomic number, and then we have capital letter K as our atomic symbol. Now, these isotopes are great in that they're going to talk about having different masses of their nuclei, essentially different number of neutrons. And it says most elements on Earth are found to be mixtures of isotopes. For example, boron is almost 20% boron 10, okay, and about 80% boron 11. So it has 6 neutrons versus 5. Now, this is called the percent abundance. Okay, in nature, if you're walking down the street, roughly 19.9% of the time, you're going to meet boron 10. 80.1% of the time, you're going to meet boron 11. And you will not know these numbers. You have to be given these percent abundances. And so, again, isotopes are atoms with the same number of protons, but they only differ by mass. And that's because they have a different number of neutrons. So if we are looking at hydrogen, hydrogen in nature naturally has 3 different isotopes. The first one, hydrogen number 1, is the most common. I know it's the most common because if you look at the mass of hydrogen on the periodic table, it says 1.0087. Okay, actually it says 1.0079, sorry. And so if we round that off, it has a mass of 1. And so the most common isotope of hydrogen is 1. It has 1 proton and 0 neutrons, okay? Because if we take 1 minus 1, it equals 0. So there are no neutrons inside protium, and it happens to be a name. These are the only isotopes that actually have names to them. Deuterium is hydrogen 2. It has 1 proton and 1 neutron. And then tritium is hydrogen 3, okay, having a mass of 3, and it happens to be radioactive. As we look at isotopes, typically, not all the time, the heaviest of the isotopes is radioactive. Now for our isotopic symbol, we're looking at our atomic number as the number of protons in the nucleus. It also happens to be equal to the number of electrons that are orbiting around the atom. And the mass number is the atomic number plus the number of neutrons, okay, because the atomic number is the number of protons. And so our mass number is going to go upstairs, our atomic number is going to go downstairs. Okay, and remember, our mass number is rounded off from the periodic table to use these. So it says how many protons, neutrons, and electrons are in carbon 12? Well, the atomic number, 6 protons. So we know there are 6 electrons, same number, and then the mass number, subtracting the atomic number, 12 minus 6, will get us 6 neutrons. Do the same thing for aluminum. How many protons are there? If you said 13, you're right, which means there's 13 electrons. And then how many neutrons? 27 minus 13 gets you 14. And then it says fill in X and Y. So here is the element iodine. And so if we look up iodine on the periodic table, we're going to see that it has an atomic number of 53. And so let's just look up the mass of iodine and round it off from our periodic table. And it rounds off to 127. So here is the isotopic symbol for the most common isotope of iodine. Now, this is the atomic number. In the boxes on the periodic table, sometimes the atomic number is upstairs in the box, and sometimes it's downstairs. So it depends upon what periodic table you're looking at, okay? And we know this is the mass number, okay? And so what we'll see is that we will need to know this atomic symbol, okay? What is the symbol for aluminum? It says, why is the atomic weight of aluminum not a whole number? And that's because not all atoms of aluminum have the same mass. And so this is what we call an average atomic mass or average atomic weight. It is not average in the sense that if you have 3 isotopes, we're going to divide by 3. It is called a weighted average, okay? And we'll look at that a little bit later on in the term in this particular PowerPoint. Now, the percent abundance of an isotope is typically given to you. And so of all of the elements, all the atoms of that element in the entire universe, what percentage is of that particular isotope? And so if we're looking at copper atoms, it's either going to be copper that weighs 63 or copper that weighs 65. And so I wouldn't even know off the top of my head that copper has 2 isotopes. You would be given that information. It's not something you can look at the periodic table and just go, oh, you have 5 isotopes. Now, in order to determine that isotopes exist and to determine their mass, please make sure that you click on the following link to see how a mass spectrometer works, because you're going to need to know how does a mass spectrometer give us back then the masses of these isotopes, and it will also tell us the abundance of that isotope, so our percent abundance in nature. And so these machines are great tools in order to determine small masses. Here at Edmonds Community College, we do actually have a mass spectrometer. We haven't got it up and running and using it yet, but we do actually have it. We have tested it. It's a great machine. I love it. But we want to utilize this in lab. So when you move on to general chemistry and organic chemistry, you're probably going to meet our mass spectrometer. And so it will tell you something about the mass of something you made in lab. All right, so that is section 2.5. I'm going to break here, and we're going to talk about the periodic table in the next video so that we don't OD on me talking to you. And so, again, thank you for joining me for section 2.5.